All right. Hi, everyone. Good morning. Let's see. If you're attending online, I ask that you open your camera. We're gonna today finish. So my goal for today is to finish the regression exercise. We're gonna be able to compare all those models and talk about them. And then I think we're gonna have time to quickly go through a lecture, which I realized was actually better if I had given you before the actual lab of the regression exercise we're doing. But anyways, we're gonna go through that just to make sure that you understand some of the concepts of, especially about what are these models telling us, what are those parameters and how they relate to our measure of interest, which is response of yield to seeding rate in this case. And then I think we're going to still have a little bit of time at the end to talk about the exam if anyone has any questions about it. So that's my plan for today. With that, if you have not opened yet your project for the regression exercise, please go ahead and do that. I'm going to do on my side here as well. So let's see here. Maybe I can gather just from my code. But I believe we finished the intercept only and the linear regression model. I think we stopped here, right? Is that where you all have as well? Okay, so right now in my environment, I don't have any variables, which I hope that's the same on your side, or at least that if you have that you created today and not carrying over from another day. But for us to be able to run things correctly here, we're going to have a few objects from the beginning. So I'm just going to come back and run the library chunk. And then the dataset chunk, the reg DFW. And I think that's all we actually need because everything else we were just exploring different things. I think we're also going to do a model comparison at some point. So we're going to have to have, yeah, we're going to have the model. So make sure you run the mod1int chunk. So we have that model there. You don't have to run the model assumptions for that mod1. So next thing we're going to go is to the second model. Oh, we also need to create the ND. Sorry, so that's the first time we create ND. So this is the chunk that's named ND, and it is under, so the model 3 intercept only all the way to the subheading final plot. There's an ND right there. We want to run that. Well, yeah, we're going to have to run this chunk as well for the better final plot. You know what? I think we may actually be just easier to, yeah, okay. You know, to make sure that I don't lose anyone here on my chopped chunks running. Let's just come to the 5 quadratic model. Once you are in that chunk, just run all above. You may take a quick moment here because of the bootstrap at some points, but that's fine. So as that's running, I just want to remind you, so with this exercise here, what we're doing is basically trying to find the one best model that we're going to use to find the optimum level of seeding rates that optimizes yield in this case. And we already talked about that this is an overall concept that's very common in agriculture, and you may already be familiar with this in your own area of expertise. So you may think of, you know, anything that you're changing input level and expecting a response on some output variable that you're measuring. So All right, so I'm on my side, it finished running, so I'm assuming that it may have finished on your side as well. If that's not the case, let me know and I can give you a moment here, but if I don't hear anything, I'm just gonna assume you have everything and we're gonna keep moving. All right, so we ran the intercept only model, we ran the linear model. Now we're gonna run the quadratic model, right? So we talked about that response may be quadratic, and sometimes it's not as simple to just look at that scatter plots of input and output and make sense. So fitting a model can help us to perhaps see that. All right, so the first time that we're going to run a quadratic model, at least in this class, I think is going to be interesting for you to notice how that happens. So we're going to come here, make sure you run that options for the contrasts to change to sum to 0. And on mod 3 quad object, this is where we're going to specify our actual model. So if you want to start coding with me, we're going to keep using the function LMER. If you remember, we're using LMER here because we're treating block as random in this case, and because we have other components of this model that are fixed, we need a modeling function that incorporates both fixed and random effects. LMER is one of those functions. This is a great exam question, just so you know. All right, so we're still, I just want to print our data set here just so we can see the columns again, column names. The data set name is reg_DFW. I'm just going to print that below to inspect the column names. We just have 3 columns here. Rep as a factor, sitting rate as numerical, and yield as numerical. So we're going to have yield, tilde, meaning explained by. And then the first thing I want to give here is just our random effect of block. If you remember, the way that we specify a random effect is by placing it around quotation marks, giving a 1, a vertical bar, and then the column name that we want to treat as random, which in this case is rep. Now let's give the fixed effect part of this model, which is really interesting because before up until this point, I guess we've been thinking on the ANOVA setting where our explanatory variables were all categorical or factor. On the previous model before this that we ran the linear model, meaning intercept and slope, how did we specify that we wanted? So remember that every model has an intercept by default. That's your overall mean. How did we specify the slope in our intercept slope model previously? Anyone remember that?
We use seed rate.
Yes, so we just said sitting rate, right? This is what we said. So this is basically the same, at this point, is the same formula as we used for the intercept and slope model that we ran on the previous step. Now, how do we specify a quadratic model instead? Basically, we just have to add a quadratic term to this model. The way that we would do it, so if we add a plus, you would think that if you do something like this, so you'd say sitting rate, the same name, sitting rate, 1,000 seeds per hectare, caret 2, meaning to the power of 2. That, if you've been doing something like this in Excel, that's how you would do it in Excel. However, in R, there's one little extra step to make sure that this quadratic term is actually appropriately incorporated, which is to wrap it around a function that is uppercase I. I believe this function stands for identity, and it's just one requirement, I guess, for R to understand that you really want to increase sitting rate to the power of 2. This is basically how you would specify a quadratic function in R, right? Let's say if you wanted to fit a cubic function or any other power, you just keep adding pluses, adding that I, adding the sitting rate, caret, and then the power that you're having that function to. It's pretty simple, but this is how we would do it. Also, something for you to notice that before, when we were running ANOVA, our explanatory variables, so what comes after the tilde, they were all categorical. Rep was categorical as it is here, but also here we had sitting rate as categorical, or we had nitrogen and potassium rate as categorical. Now having that as numerical, and we know it's numerical from the data frame, is what is telling it to basically give you regression parameters instead of calculating means, or parameterizing the model to give you means when you call EM means. That's basically the difference, is how you treat your explanatory variables. And we talked about this already, that if your explanatory variable is numerical, you can turn that into a factor and get an ANOVA, just like we've been doing with nitrogen and potassium. However, if your explanatory variable is already categorical, like variety, or maybe something else that is like already a name, is not a number, then you can only run ANOVA, you cannot do regression on names. All right, so just to finalize here, we just need to call our data. So data equals reg TFW. Let's go ahead and run this. It gave us a warning here, but I think that's fine. It's just because we have the power of we squared sitting rate, and that is just it's just giving some warnings about the scale, but that shouldn't be an issue. All right, so let's ask for a summary here and see what that's telling us. So linear mix model, right, as we know, it was fitted by Remmel. It gives us here our random effects, which is basically just the effect of rep and then the residual. So remember that rep is your true random effect and residual is just that extra source of variation that every single model has, regardless if it is a fixed, a random, or a mixed model. And then it gives us here the estimates for our parameters. So it gives us the intercept. Notice again, we did not have to explicitly call for an intercept. That's implicit already there. So it gives us the estimate of the intercept, the estimate of the sitting rate, the linear part of that equation, and then the curvature of that quadratic term. And if you notice here, intercept was not significant, but then the linear part of that and also the curvature were significant. All right, I guess any questions about what we're seeing here? So yes.
What if we have another experimental design? In this case, we have RCVD, but what if, as we saw with the split plot, what if we have a split plot design? Can we run still like some kind of regression? If so, how do we specify it in the random effects? Do we follow the same structure?
Yeah,
so
so
from the big plot to the small one to the small one?
right. Yeah, so if we had, it's actually going to be a little bit different because if you did have a split plot on this type of study, you would have to have your random effects. So you still have to specify here. So let's say if we were to go back to our potassium and nitrogen example, treating that as a split plot, you would have to have a categorical column for potassium that could come on the random effect, and also a numerical column for potassium, which would come here on the fixed effect part. So it would be a little bit different because one of them is just setting the error level, and the other one is actually calculating the fixed effect estimates of the model, right? So it would be a little bit different again because you would have to have a column where you treat potassium as factor, so you could use that on the random effect part, and then also a column for the potassium as numerical, so you could fit here on the fixed effect part of it. So it'd be a little bit different, but still the concept of it would be different basically on the random effects, right? Because we have to specify that error structure, but it would be similar on the fixed effect part where you have to have it numerical to calculate those regression estimates.
Yeah.
Awesome.
Dr. Bastos,
Yes.
like in case of like split plot, is there any way we can make by like combining the treatments, like making the treatment combination? the column for the treatment combination and count it as a, like a numeric term.
I guess I'm not fully sure I understand your question. So you mean like, I guess what treatment combination are you talking about?
I mean, like for the in case of nitrogen and potassium, we can make the like a treatment combination of the nitrogen and potassium, right?
Yeah. Yeah, so in our specific case that we were doing before, because we have two potential numerical inputs that we're changing, then the actual analysis would be more of a response curve type of analysis rather than, so this type of analysis is when you have one input. If you have two inputs, then it becomes a response surface analysis, which is a little bit different, and the way that you analyze is different than just for one input. But we're not seeing that in this course. If you have that in your research and you want some resources, I can definitely share some resources with you. Yep, just let me know. All right, so remember that you will be asked to interpret things, different types of things. One of them could be this estimate summary here, and what does that mean? Right, so in just looking at even though I am a big proponent of making plots to visualize relationships rather than just relying on numerical summaries or tables, you still may be asked about this, right? Well, I guess not in this exam because this is not going to be in the midterm, but maybe on the final. Right, so if you're seeing a seeding rate linear component that is greater than 0 in this case, what does that mean? How do you think it looks like? So this is basically telling you that there is a positive relationship here between seeding rate and yield, right? At least based on this slope estimate of the model. And then if you have a negative estimate of the quadratic component, it basically means you have a point of maximum, right? If this estimate here was positive, this quadratic estimate was positive, it would mean you have a point of minimum instead, right? So perhaps the direction of these estimates, just by looking at them, give you some information about what is this relationship. Again, I would always recommend you plot them to actually see what's going on. But just by looking at them, you should already expect what type of relationship it was modeled here. All right, so we're going to check our assumptions. As always, I think all the code is there, so you can just go ahead and run it. So we're just using augment to collect all of our residual information along with our original data frame, and then calculating these standardized scale residual here. We're checking first our residual, so fitted by residual plots that we've been looking already. And I really want to take a moment here for us to stop and appreciate what is going on here. So if you have this, so remember now, this residual is coming from the quadratic equation. Let me go to this residual was the one coming from the linear. And these were the residuals coming from the intercept only. Let me see if I can have them all kind of side by side. So maybe let me rearrange as well so they are in the order that we ran. So first on the left, I had the residuals for the intercept only. Then I had the residuals for the linear, and then the residuals for the quadratic. Again, I want to talk again about the fact that the reason why we check assumptions on residuals is because residuals change, raw data does not, unless you remove data for some reason. But in this case here, our raw data is not changing, right? We're only changing the model, and changing the model, we're changing the residuals. And that's why we check assumptions on residuals, because the residual is that interaction between your data and the model. So if you change the model, you're going to change your residuals. So if we were to look at these assumptions here, notice again, it's the same data set. We're just changing the model, right? So on the first one here on the far left, we have the residual fitted by residual plot for the intercept only model. So look, we see this pattern here of increasing the magnitude of the residual as the fitted value increases. So maybe this could show up in different cases. It doesn't only have to mean that if you see this, it means your model is underspecified. But in our case, we know it was because we already had a scatter plot of our relationship. We knew that looked quadratic. So if you just fit an overall mean, it's not going to be a good fit to the data. So here the residual is telling you, hey, maybe add a slope to your model, because right now you just have an intercept. Maybe add a slope to fix this increasing slope of your less relationship on your intercept only model. So then we fitted a slope. So then we come to the top right residual. We fit a model that had an intercept and a slope, and then the residuals they changed and they look quadratic now. So maybe the residual is telling you, if your residuals look quadratic, try to incorporate a quadratic term in your model and see if that fixes it. So that's what we did. And then we get, lastly, these residuals here, which are coming from the quadratic model that we just ran. So, a lot of things here going on. One of them is perhaps we saw that there was this clear pattern in residuals in the first two models. One of the ways you can fix this could be by specifying a model that better fits your data. Again, that's not the only solution. You may have other issues with your residuals that just changing the model, how many estimates you have in the model is not going to fix it. There are other remedies for different problems in residuals, but this could be one of them. If you see your residuals have this clear pattern, maybe it's indicating to you that you should add that parameter to your model next. And then as we run our quadratic model, now we see that our residuals are looking a lot better than the previous two, right? So now our blue line is fully intercepting the 0 line, which is what we would like to see. And then we don't have anything plus or minus 3 here. So no outliers, no pattern, clear residuals here, right? And yeah, I guess this is a great exercise for us to understand that residual is what we use to check assumptions. And one of the ways that your residuals may be telling you that you need to add a more complex model to your data for that to become a good fit. And this is one way that we can visualize that. All right, I'm going to close. Yes, Comfort.
Yeah, I have a question. So in this case, because you usually say something like the data doesn't change, it's the model you can change, to make the maybe residuals better. So because I hear of things like you can transform your data, maybe using logarithms or something. So would you advise like we changing the model first, like using this quadratic stuff, maybe in other cases than first transforming the data? But what about cases where we have categorical variable?
Yes, so that's a great question, Comfort. I think it used to be, and it still is to some extent, common to teach data transformations to force your data to fit into the model rather than the model fitting into the data. What I think it's more advised these days, because so when we were doing model transform or data transformations to make the data fit the model, it were times where we did not have the computational capacity we have today. We did not have computers that could do all this. So it was a lot of statistics by hand pretty much. And transforming the data to fit the model was the easiest and sometimes the only solution for that. Now we have other modeling tools that can help us first play with the model and help the model to fit the data. In this case here, it is a case where we're playing with regression. So with regression, you could play with the model specification like we're playing here, but it could also be other things. So we could have, for example, if the residuals show the heterogeneous variance, there is a whole set of modeling approaches we can deploy to help with that. Also, a lot of times what happens is we may be running a linear model on data that is not supposed to be used with a linear model. So for example, one very, very easy example for us to think about here. So linear model is basically used for things that are really not bounded. So there's no limit to the magnitude of the response variable, especially. So think about yield. Yield is bounded by 0, right? You cannot have negative yield. But normally we're collecting yield data that is so far from 0 that doesn't impact what we're doing. However, if you're analyzing, for example, percentages or proportions or things like that are still numerical, but they have a boundary, a very clear boundary, right? Like something that is a percentage, at least you would imagine it would be between 0 and 100, or maybe 0 and 1, right? So it has a clear boundary. And even though you may make a density plot and the data may look normal, but the data generating process is not unbounded, meaning that maybe using a normal distribution to characterize it is not the best. So that in those cases, we would use generalized models, which basically allow that the assumption of the distribution of the response variable to not be our normal distribution that we use here by default. So if you have things like, so if you have proportions, or if you have count data, or if you have percentages, then we start talking about distributions like Bernoulli and logit and different types of distributions of the response variable that is not necessarily a transformation to the response variable. It's more a flexibility on how the model is treating that response variable. This is a conversation that goes a lot deeper than what we can develop that in class. But basically these days, instead of transforming the data, you would basically try to use a different model approach, which could involve perhaps using a generalized model that does not assume that your response variable was generated by a normal process in the sense of creating a normal distribution, but was rather using a different distribution that generated the data, like count data, percent data, and so on. So I guess taking another step back and trying to summarize all this, I would first recommend that you look into the modeling aspect first and trying to find a model that fits your data the better, either by changing the parameters of the model or maybe by changing the assumption of the way that the response variable is distributed, and try that first. I think that's what I would do on my side. And then if you try that and it still doesn't work, for whatever reason, then you may still have to rely on some methods that were more common in the past. Yeah, so I would say focus more on the model and less on the data. Make the model feature data and not the data feature model first.
Thank you.
Thanks, Comfort. All right. So yeah, I just have some notes here for you that, that with the same data, we're creating different residuals because we're changing the model. And I think we talked more about this in the CRD videos, which again, all of you may not have watched it if you did not do the exercise. But what a residual is basically the difference between what is observed, so the point data, and what the model is predicting, which is basically the regression line the model is fitted to. So a residual is just the difference, again, between the point and the line for all the points. So if you're seeing a pattern in your residuals, it may mean that if you add that quadratic, in this case, a quadratic term here, maybe that is going to change, right? It's going to fit better your data, and therefore your residuals were not going to show the pattern. All right, so we just coming back here to this plot. So now we do not see a pattern like we were seeing before. And again, remember that same data, different model creates different residuals. We're checking the QQ plot as well. It looks even better than before. although really the main difference that we see is on the fitted by standardized residual, but on the QQ plot, we also see that is the points are closer to the theoretical line. Now checking our random effects, I think I left you the code as well. We can just go ahead and run it. Again, just 4 points. It's difficult to really say much, but they look okay. Then I'm just calling again our summary for us to take a look again at our model estimates. So our fixed effect estimates. So we have an intercept, we have a slope and a quadratic term, and our slope and quadratic are highly significant. Our intercept was not. And then we have here a final plot. So basically, I'm still using the same code as before, where we're using on the augmented data set with the residual information, we're using that .fix column, which comes from the augment function to make this plot, and that's what it looks like. We've been using this column for the previous models as well, just as a reminder, but that's how it looks like right there. And so the thing here is that this is not really, it doesn't look like a continuous regression line, right? And the reason for that is because our model the model was trained on 1, 2, 3, 4, 5 seeding rate levels. So it's basically predicting that fixed column coming from our residuals is predicting what would be the response only at the levels that it was trained on. And that's why it looks like segmented. Although in theory, the model is not segmented. It's a model that can predict any value within the space of our data. Also, it does not have any confidence intervals. So solution again, I want to create a smooth line here. So making this green line smooth instead of segmented like it is looking right now. And then also add a confidence level with Bootstrap. It's very similar to what we did before. So we're creating two things here. So remember that ND has 81 seeding rate values from 40 to 120, right? So we're just creating that fake data, I guess, to ask for a model prediction for each one of those levels to make our visual line more smooth on the plot. So right here on this first part, we're just getting for the prediction for the model for each one of those 81 seeding rate levels, which is just the mean prediction, right? So it would basically be the line, this line here, but is smooth. And then the line itself is not enough. I do want to take a look at the confidence level around the line. So then we're doing Bootstrap, which we've been doing for the previous models as well. I think I left you all the code there, so you can just go ahead and run it. And once we get that, we're just combining the confidence, the 95th confidence interval for that predicted mean. We're adding that to ND, just so we can plot it. So if you run that, and now you run a ggplot, it should look like this. So again, this green line here is coming from this geom line right here, which is creating a line for you, but it's basically a whole bunch of points. If we were to change, I'm just going to change for you to notice. So if I change from geom line to geom point, those are just all the points that we ask for a prediction from 40 to 120, all the 81 points. But then we're showing this as a line because it is a regression line, so it makes more sense. But I just wanted for you to understand that the line is just connecting each one of the points. And the reason why I wanted 81 seeding rate values here is because the more you have, the more smooth this line is going to look like, right? So let me just change this back to geom line. This is one of the easiest ways for you to show a regression line on a plot, is you create fake data with a lot more levels than the original data you trained it, and then train the model, and then ask for a prediction on this fake data. There are other ways you could show, maybe even directly modeling in ggplot. I would not recommend that. It's complicated and prone to some errors. So the easiest way to show your regression line results is train your model or run your model, then create some fake data with the mean and max of your X variable, and then just ask for predictions of the model. Yep.
I think some concept, like the question, make sure I understand. So that line is basically the model.
Right.
That we chose, and the dots individually are the data. The distance between those dots in the line, that's
Right.
okay.
Yeah. Yeah. So Zach was asking here about maybe the concept of residuals, right? So again, our residuals are the difference between, so the line is what the model is predicting, right? That's what the model is telling us. And then the points are our observed data. So residual for any model, including our ANOVA models, will always be the difference between your observed data and the predicted value coming from the model. Where the predicted model coming from the model will always be the line, right? That is the prediction. So if you give if you give a sitting rate of 60 to the model, it will always predict a yield which is what intercepts with this green line. That's always the prediction it's going to give you based on this model, right? Even though in our data, we see that there's variability around that. And that's why the model is the mean response. As you can see, the model is trying to pass through the mean response across all points, right? Okay, so I hope that by now it's pretty obvious to you that the best, at least of the models that we tried, the best one that fits our data the best is the quadratic. Also, something for you to notice is that the intercept model, the intercept plus slope model, were all significant. The p-values were all significant. So always remember that because your p-value is significant does not mean you have a good model. You really have to plot and see and understand and play with some different functions or models that make sense to really be able to tell. I guess in this case here, just from the initial EDA that we did, we already hypothesized it was a quadratic was the best fit, right? But again, sometimes this is not as clear. Sometimes your cloud of points is really messy and just visually inspecting is harder to see. You really need to run models to give you that insight. So if we were to choose a model, at least among these three, to make a prediction on the effect of sitting rates on yield, we would use the quadratic one, right? That's the one that fit the best, at least visually. All right, so in our data set, we know that there is a yield response to sitting rate, because maybe it could be the fact that we didn't have a response, like we saw that intercept only model sometimes is the best model. Sometimes you don't have a response to your input variable, and that's okay, right? In our case, we know there is a yield response to sitting rate, so the intercept only model is not a good candidate. We know we achieve a maximum point. So our linear model, linear in the sense of intercept plus slope, is also not the best because it does not characterize that plateau, right? So we know that there is a plateau. We ran our quadratic model, or we know there is a point of maximum, perhaps is the best way to say this. We ran our quadratic model, and this is what it's looking like. So we have a point of maximum, and then its yield starts decreasing after a certain point. But then I still want to show you the linear plateau model. That is another option that we have here, and it's going to be the first non-linear model we're going to be running here. So after we finish running the fourth model, then we're going to do comparison of all models and see which one at least has the best fit metric that we can use. All right, so one key difference here is the terminology of what is a linear model and what makes a nonlinear model and how are they different. We're going to see better this concepts on the lecture that I have following up this exercise, but basically, I think there is some confusion here, and I've been confused for some time. You may have been confused maybe until now, but saying that a model is linear really doesn't have much to do with the shape of the curve. So, for example, let me just show you here maybe so the intercept only here, if we look at the final plot, which is this is a linear model. Yes, it is a linear model. I guess this perhaps is obvious with what you've been thinking. If we look at the linear model that I'm calling linear, which basically is intercept plus slope, if we look at that final model or final plot, it is a linear model. Now, if we look into the quadratic model, let's take a look at that final plot. Would you say that this is a linear model or not? Priscilla, what do you think? You don't think it's a linear model?
Well, it's just that in my head, when someone says linear, like I'm picturing something like completely, not straight, but like,
Yeah,
you know.
perfect.
I can't find the right word to describe it.
Yeah, that's perfect. And so Priscilla was saying here that when she thinks of a linear model, she thinks of something that's straight, that doesn't have curves.
Yeah.
And I totally agree with you. I think that's also the way that I used to interpret this, and I think a lot of people do. So this model is also a linear model. So the what makes a model linear or nonlinear is how the model parameters are estimated, which we're going to see now. The linear plateau is going to be the first nonlinear model we're going to see here because it has nonlinearities in the parameters of the model itself and not in the way that the model looks like once it's fit to data. I think it's a very common perhaps misconception or misunderstanding that I also had for the longest time. And I think that normally we have this misconception, and that's why I'm just wanted to bring this up. So all these models are linear, not because of how they look, but because of how the parameters of the model are estimated. They're all estimated in a linear fashion. So our first model here is going to be a linear plateau model, which if you remember, linear plateau is going to have a break point pretty much, right? So it increases until a certain point, then it breaks, and then is a plateau after that. That's what's called linear plateau. So let's fit our first nonlinear model, and I think you're gonna be able to realize why it is a nonlinear model. So if you come here to the chunk, let's give it our get symbol. We're going to be using a different function now because it is a nonlinear model. We're going to use a function NLME. So a nonlinear mixed effect model, I guess is what this stands for. I want to again print our reg underscore DFW so we see variable names again. So yield is going to be explained by, and then here there's something very different. We're actually going to be calling a function that is going to help us to estimate the parameters of this model in a nonlinear fashion. So this function is called sslinp from the package nlraa. So here we basically now give, so we notice that yield is our x variable, is our response variable. Or I'm sorry, our y variable, our response variable. Now we're gonna, inside of this function, we're gonna give our explanatory variable or x variable, which is seeding rate, just like we were doing before. And then you don't know yet, and you would know, the way that you would learn this on your site is you would basically Google this and read documentation and maybe some papers, but this nonlinear function here, so it has an intercept, it has a slope, and then it has a breakpoint on the x-axis. So those are called A is the intercept, B is the slope, and then XS is the breakpoint on the x-axis, after which you don't see a response anymore. So we have to call those here, A, B, and XS inside of this sslimp function, just to say that we're basically just adding placeholders here for the function to iteratively estimate those for us. Notice that seeding rate is what we actually are given it is a column in our data set, but A, B, and XS are not columns in our data set. These are parameters that we're asking for this function to iterate over and estimate for us. I'll be with you just in a second, man. And then the reason why I know that A, B, and XS is what we need to specify here is because if you go to the documentation of this function, sslimp, that's the function that basically fits a linear plateau. If you were fitting maybe a quadratic plateau or maybe some type of exponential function, you would use a different helper function here, and it would have different parameters that you would like for it to estimate for you. Yes, Aman. It could be the negative. Yeah, I mean, it could. So if, it has happened with some data that I play with, that if your response is actually like negative and then it reaches a plateau on the bottom side, then it would basically, you have an intercept, a negative slope, and then a breakpoint that once you plot it, you would see it's on the lower side. So it could be like a negative or a positive linear regression. Yes.
So is breakpoint like, is that same as a global minimum and global maximum?
So global minimum, global maximum, it could be ways for you to refer to it, right? So I mean, just like in the same way, so if we go back to one of the first chunks here, where I was showing this. So if you think a quadratic curve, it also has, in this case, a global maximum, right? If the quadratic was positive, then it would mean, the quadratic term was positive, then it would mean it would be like this shape, which would have a global minimum instead. With linear plateau is the same concept, right? I guess the main difference here is that on the quadratic, you are expecting that after the optimum, if you keep increasing, you're going to start seeing a decrease. Whereas with linear plateau, you're assuming that after the optimum, it just doesn't change, right? And those assumptions can be either biological or statistical. Biological, you will always, at some point, start seeing a decrease after an optimum, right? But statistically, with your data, it may be that the linear plateau is the best fit, even if you're working with a biological system. And that may be just because you did not have enough high levels of your X variable to actually start seeing a decrease, right? All right, so let me come back here to our linear plateau where we're specifying the model. So this model here, so after that SS lin P, if you add a comma, give a few breaks so we can do some coding. So we're going to specify our data. So data is going to be equals to reg underscore GFW, the same as before. And then there's going to be a few different ways here of how we want to treat things. So I want to create our random effects. So it has is a little bit, this function is specifies random effects in a different way, just for you to be aware. So it has an argument for random, where we're going to explicitly say what is our random. And for us to say that I want wrap to be, or our block to be random according to the parameters of this model, it's going to be different. So just bear with me. But basically, we're going to say here, we're going to give a list. So we give a function list. We're going to say wrap, which is our variable that we want it to be random, equals to, and then we're going to use a helping function that's called PD diag, coming from the LME package. And in here, we're going to say A plus B plus XS tilde 1. So it's basically what this function is doing is creating a diagonal matrix saying that for wrap, I want the effect of the parameters that the model is calculating for us, which is A, the intercept, B, the slope, and X as the breakpoint, to be random in respect to rep. That's what we're saying here. It is a different way of saying this. You may not see this type of specification unless you use an LME, but that's how we would do that. And then finally, because we want an actual estimate of A, B, and XS, I want to know what is that number, we need to say that they're fixed effects. So we give a comma, there is an argument for fixed. We're also going to give a list. So I want to say A tilde 1, comma, I'm going to break line just to make it more readable, B tilde 1, comma, XS tilde 1. So this again is just saying on the fixed part of the model that we want an estimate for A, B, and XS. So basically we're specifying our random effects, our fixed effects, and then another difference that there is here between linear and nonlinear models is that with every nonlinear model, it will iteratively try to estimate for us, in this case, A, B, and XS. but we need to give some starting values for it. Because if you don't give starting values, it may have a hard time to fit the parameter space and find that by itself. And so we have to provide some starting values. So there is another argument called start that we're just going to use the C function now and say A equals to, I want to say A equals to 0, B equals to 0.3, and XS equals to 100. So these values here, I basically am telling you of what we're using. If you were doing this for something that you're doing on your own, how would you figure out your starting values? So remember that A is the intercept. So even if we just went back to any of the previous models, let's say the quadratic model, and we were to look into the summary of that model. Let me find that right here. So we see that for the quadratic model, the intercept is about -1. So 0 is not a bad starting point. We see that the slope of the quadratic model is 0.3. So that's why I have my slope as a starting value of the linear plateau as 0.3. And then the breakpoint is what you would, let me just get one of the plots here to show you. So the breakpoint is on the x-axis, what's the breakpoint? So here we kind of, even from the quadratic, we kind of looks like our breakpoint is around maybe 90 or 100 on the x-axis. That's what XS is. So just by visual inspection, that's one of the simplest ways for you to get some idea of what starting values you would like to say here. If you try those and they don't work, you can play around, right? You can, if you try them and the model says it did not converge, you can play around with different values and try to get the model to converge. But that's what I want to try first. So let's see. I lost. Okay, so I ran the model. I did not get any errors. If for some reason the model did not converge, you would tell you convergence was not achieved or something like that. So you would know that maybe you have to change your starting values. We did not get that error, so we went through. So we can go ahead and ask for a summary of this model. Even the summary looks a little bit different. So now the first panel here is basically just, I guess as far as we're concerned, we're just getting a standard deviation for A, B, and XS coming from that random effect. If you come on the second panel here, we have AIC, BIC, and log likelihood. These are just model fit metrics that we're going to talk more in a second here. And then we have this data frame, which is just so the value here is the actual estimate of what the model found. So intercept, if calculated to be 3.45, the B, so the slope calculated to be 0.13, and the breakpoint to be 73,000 seeds per hectare. And then it gives us an error and then p-values. Yes, somebody has a question?
Dr. Vestas, I'm getting an error. Is saying that error in grad, then third bracket, comma, NM subscript out of bounds.
Okay, so,
Instead of I use that plus BDI, so
you mean here? Yeah, Shakir, I think it may be something with your code that maybe you forgot something. I would say, so if we start from the beginning, make sure that all the sitting rate, A, B, and XS have a closing parenthesis right there, and then you have a comma, that you're random, that you have rep equals to pdiag, and then A plus B plus XS tilde 1, and you close both of your parentheses here. I think it's probably a parentheses or a comma that you have either extra or don't have. So take a look at my code and see if you can find what's going on. All right, so I'm gonna check here if you want to take a screenshot just so you can look for longer, because I'm gonna move on here. But
Okay.
yeah, if you're still having issues after looking over this, let me know.
All right, thank you.
All right, thanks. All right, so then we have, again, our estimates here of A, B, and XS. Notice that these estimates are basically iterations that the model ran for us to look for these values. They're going through an iterative process because it's trying to optimize all three estimates at the same time with your data. And that's why we have to give starting values. And then in this case, we use this sslinp function to do that for us. All right, so let's check model assumptions. I left everything for you there. So not much to do, just run it. Again, it's just using the augment function to get all the residual information alongside with our original data set, and then getting standardized residuals mostly for outlier detection. Now, if we make the plot of our standardized residuals versus fitted, it looks good as well. You know, I think it looks pretty similar to the quadratic actually, right? And so that's a good sign. It means that this model is also a good candidate. If we do the QQ plot, same thing, right? So it looks perhaps even a little bit better than the quadratic on the QQ plot. So residuals are normal. Now checking our random effects. I think I have left a little bit of coding for us to do on this chunk. So here, if you come to this chunk, we're going to extract the random effects of this model by using a different function. So now we're going to use a function called run, or actually, well, it is a different function because it's coming from a different package, but it may have the same name as before. So runf is the function we give the model name, so mod4_linp. If you just run this and then you print that object that we created, mod4linp runf, you notice we have a random effect for each one of our model parameters. And this is not a data frame, it's an array, I believe. So we need to just transform that to a data frame. So give it a pipe and as data frame so we can actually plot it in ggplot. So ggplot works with data frames. So after doing that as data frame, then this is what we get. And if you just run the plot below is a QQ plot for our estimates. So what's happening here? One thing is if you look into the data frame that we created, it has an estimate here for each term and then for different reps. When we make this plot here, is basically showing all those terms together. So A, B, and XS, all the residuals for them together in one plot, which is not what we would want. We actually want to see one of these plots for each one of the terms. So showing you again the data frame, we have a column called term where we have A, B, and XS. How can we change this ggplot code to make it give us 3 plots, one for each of the terms?
Facet.
Yes, facet, right? So let's go ahead and add a plus, give a facet. We can use facet rep this time. Just give a tilde and the name of the column is term. So this is what it looks like. It basically showing us, so this, sometimes you may see this type of QQ plots on your random effects. And what's going on here is basically, so the A term, which is the intercept, it was able to calculate a different random effect for a different random effect estimate for different levels of A in different reps, because that's what we asked. So that's why you see the QQ plot line and the points there. With B and XS, what's happening here is, and you see this in cases where the variance of that factor is so small that it was actually not able to estimate a difference variance for different Bs coming from different reps. It basically estimated a fixed variance across them. So that's when you would see a QQ plot that looks like this. There's nothing wrong with it. It's just saying that the variance of B inside reps is so small that it was not able to estimate different variances for different Bs. That's basically what's telling us here. So it looks worrying, but nothing to worry except for the fact that there is not a lot of variance here, which is actually a good thing for us in the case of B and XS. All right. So I think I want to finish here the linear plateau, and then I'll give you a break, and then we'll come back and do model comparison. So now if we just check the summary again, we see here that A, B, and XS are highly significant on the p-values. And then if we take a look at a final plot, this is how that looks like. Remember that I'm still using that dot fixed column of the augment, and that's why the line looks a little bit choppy, right? Because it's kind of breaking at the points where we had data. We already talked about this on the quadratic case. We can, I guess, fix this visualization by using the model to make a prediction again on all the 81 levels of seeding rates that we created in our ND data frame. So let's do that. So we run here your ND again to get the mean prediction based on this model for all of your 81 levels of seeding rate. We have to specify a slightly different function here for the nonlinear to make a prediction on the confidence intervals. So just run that function and then run your bootstrap function there. May take a moment here just to do all the bootstrapping and give us an answer. It finished running for me. After that, you just, again, bind those columns of the lower and upper confidence levels to ND again, and then we can make a final plot and actually visualize this a little bit better. So this is basically the way this plot looks like, right? So we see here our positive slope and then a breakpoint around 73. And then we have the error associated with that breakpoint as well. You see that our bends are not consistent everywhere. This is partially because, or it is because of the bootstrapped confidence intervals that we just created. And then we see that so a key difference here between our linear plateau and our quadratic model is that the quadratic, so the optimum was a little bit higher, was closer to 90 perhaps, and it was modeling a decrease afterwards. The linear plateau model finds a breakpoint that is smaller, so at around 73 here, and then it finds a continuous response after that, right? So these are just these two models, how they are parameterized and how they're different. Okay, I think this is a good stopping point for us to take a quick break. So let me give you 5 minutes, and then we'll be back to continue with model comparison.
Dr. Bestos,
Yes.
so I compared my code with yours. It's exactly the same. So I don't know why I'm getting this error. Can I share my screen with you?
So let's do this. Why don't you open an issue on GitHub, and then Amrinder is going to take a look at that and be able to help you.
Okay,
And
got it. Thank you.
I'll take a look at on my side as well. But if in case he cannot, then I'll jump in. But he may be able to help you as well. Just a sec. Hey Amrinder, Shakir's going to make a post on GitHub. Can you take a look and see if you can help him on the code? And if not, then let me know and I'll jump in as well. Yes, Madhuparna.
Is totally different. Shows me in the geometry.
Okay, so it did not find this.
Object here.
So do you have that, like, so what, saying that you don't have that object, then what I would try to do is to look to see if I have it.
Okay.
Right, so go on the chunk above to see if you created that object. Because I think we created that object on the chunk above, so maybe you forgot to run that piece of code and that's why it's not there. All right, so our timer is up. So let's keep moving here. So we basically trained or ran 4 different models. And now our goal is to compare those models and choose one that is the best one for us. The first thing I want to do here to compare the models is to plot them. So I'm starting here. If you just run that comparison plot, it's just our initial scatter plot. So now we're gonna start adding each one of those fitted lines to this plot. And where do you think we're gonna get that from? ND, right? So if y'all remember, ND was this single data set. Let me just print ND here. ND has 81 rows because it has all the 81 sitting rates that we simulated. And they have a given model yield, which is the actual model fit that's being predicted for that specific sitting rate. And it has that same model's lower and upper confidence level. So for model 2 has the model, the model 2 yield megagrams per hectare is also the model response, and then the lower and upper confidence level. For model 3, the same thing, and model 4, the same thing. So it's all here. That's why we were overriding on ND, is just to create all these columns that for 4 different models, it has the model fits and then the lower and upper confidence level for all of them. So let's add a plus. Let's begin here. Let me ask somebody else. Charles, what do you think? How would you show, let's begin, let's think in steps, right? So if I want to show here the line for the first model, the intercept model, and Shay already said that it's on the ND object. How would you do that here? What function would you use first? Ruben, what do you think? Aitan, what do you think? So if I want to add to this plot, so let me just remove the plus so it doesn't mess up. If I want to add here the line for the first model, which was the model intercepts, and it is on the ND object, how would you add that line to this plot? Well, what geom would you use first? Sorry, can you say that again? So geom jitter is if you want to add points and jitter them. I want to add a line.
Geom line.
Yes. I can feel other people itching to say something. All right, so geom line, right? Geom line is what we need here. It is in the data frame ND. So let's say data equals ND. Now we need to give here on the AES, we need to give what column we want on the y-axis. Priscilla, what do you think? So let's just print ND. This is what ND has. It has 13 columns. If I want to show the model fit of the first model, which column do we need? Right, exactly, this one, right? So this is what we want to go on the y-axis. The x-axis is the same as what was specified at the top level or the ggplot level. So axis tilt like this, so we don't have to change that. If we just go ahead and run that, let's see if that does what we were intending. It does it. I want to make a few aesthetics change here. So one of them is I want to change the color to be forest green is the name of this color. And the size of this line, or I think it's called line width, to be 1.5. Let's see how that looks. Okay, I'm happy with that. All right, so Micah, how would you now add the line for the second model? I'll give you a quick hint here that you can basically just recycle this code. So we can copy this, add a plus, and paste it. And now we're just going to change, well, let's begin by the column that we want to have here to plot the line fit of the second model. So if we print ND again, that's our data frame. You know, if you, I mean, we have 13 columns here, but what would be the column that we need to actually show that line for the second model?
Mod to yield MGHA.
Yes, this one, right? So this is how we were calling the mean predictions, right? Every time that we're making mean predictions, I was calling just mod name and then changing here. So we can change that on the Y here of the second geom line. And then I just want to change the color to something else. We can do blue, perhaps. So if we run that, then this is what it looks like. Now I'm just going to keep adding for the other ones. So I'm just again going to copy the geom line, add a plus, paste it. The third model is going to be on the Y. You just change to mod 3, and then we can change the color to purple. And run that. This is how that looks like. And then finally, add another last plus, paste again, and then mod 4. And I want that to be orange. So this is how visually our plots look like. It gets really difficult, I guess, to make a lot of sense because there's so many lines and, you know, at least my brain has a hard time to understanding altogether which line fits data best. But at least I wanted to show you how you could bring all these lines into a single plot if you wanted. So again, that's why we were creating ND in the beginning and just overriding on it. It's just so we could have a single object that had all the model predicted values and also the confidence levels for each model. All right, so we assessed visually, I guess, you know, we were already at least hypothesizing that quadratic was the best. By this visual assessment, it's really hard to tell which one is the best because again, it's kind of busy. But I would still perhaps hypothesize that quadratic is the best. So now we're going to use a function to compare these on a table format and using a different metric. So we're going to use a function called uppercase IC underscore tab, which is coming from the NLRAA package. And we're just gonna give here the name of the model objects. So it was mod1 underscore int was for the first model, mod2 underscore lin, the second model, mod3 underscore quad for the third model, and mod4 underscore lin p for the fourth model. If you run this, we get a few different fit metrics here. So we have each one of the models. It's already ranking for us, I believe, in the order of the lowest to highest AIC. So if you've never heard of AIC or BIC, those are just different types of information criterion. So if you have the same data, you're just changing the model. AIC can help you to understand which model has the best fit. And you can think of, whoa, I could have used R square. Yes, that's true. You could have used R square, maybe RMSE or something else. I'm showing you AIC here because AIC and any of these metrics, so AICC or BIC, which stands for Bayesian Information Criterion, are all information criterion that take into account how many variables you have in the model. So a quick explanation of that is if you take so let's say that you measure yield and then you measure a whole bunch of things with that. So maybe you measure 30 soil variables and maybe some weather variables and maybe other things that you measured. If you just look at R square, the more variables you put in that model, the higher R square will be. That's how it goes. Even if some of those variables explain very little information about your response variable. However, AIC and AICC and BIC, this information criterion, they take a penalty for each argument you add in the model. So if you add another explanatory variable on your model, your fit metric will only improve if the amount of information or the amount of variance that that extra variable is explaining is higher than the amount of degrees of freedom it's consuming. So it has a penalty, meaning that if you add something here that explains yield very little, or maybe not, there's no relationship at all with yield, your fit metric will actually decrease because you're consuming degrees of freedom and not explaining much by adding that variable. In our case, we're not doing that type of exercise where we fit a lot of variables. We just have seeding rates and then maybe, a few parameters on the linear plateau. So, but the concept here is your fit metric only improves if you're looking at AIC, AICC, or BIC, if the amount of variance that the extra parameter that was included in your model is actually worth it. If you added something that did not explain much else variance, then your fit metric decrease or your fit metric deteriorates. And I'm saying all that also because AIC, AICC, and BIC, the lower, the better. So models that have the lowest value here would be the ones that you would say that model has the most, at least of the models that we tried, that model was the one that fit the data the best. So in this case here, very surprisingly, I think, to me at least, the linear plateau had the lowest AIC, and also the lowest AICC and the lowest BIC. It doesn't always happen this way. Maybe sometimes some of the rankings will change depending on which one of the three metrics you look into. BIC is more conservative. AIC is more liberal, I guess. But regardless of which one we use there, all of them agree that the lowest metric value is from the model linear plateau. So based on this, if you were purely using statistics to decide which model you would then use now to estimate your optimum, then we would go with linear plateau. And that's what you would use to carry your further analysis. Yes, Omar.
So I'm wondering, like, all these three columns are used to understand which model fits the best. So should we go just with AIC or consider other two as well? And if other two as well, then if one is high, one is low, like how do we navigate in that situation?
Yeah, so normally, so AIC is normally more liberal and BIC is more conservative. AICC is just a transformation of AIC that makes AIC a little bit more conservative as well. I guess normally what you would see is regardless of which one you use. So in our case, it doesn't matter which one we use. The answer is always linear plateau. If you check that value for linear plateau is always the lowest among all the models within the column. So in our case, it wouldn't really make a difference. But if it makes a difference, you know, if you run for another data set and the ranking changes depending on the metric, as long as you choose one metric and explain that you use that metric, you should be fine, right? So on a paper, for example, you could say like the best model was selected based on the lowest AIC value, or maybe the lowest BAC value. And I don't think reviewers have an issue with that. As long as you choose one and explain which one it was, and you go with that.
Thank you.
Okay, so because our model was the best model was the linear plateau here, I want to propose that we use that model to then estimate. So imagine again, if this study here was at a grower's field, which happens a lot, right? You may have on-farm research, a grower may be interested in knowing what is this answer to their production environment, and they ask you, what is the optimal sitting rates that I should have for my field? So now we've fit all these models, we've found the one that fits the data the best. Now we need to use that model to give an answer to that grower. So if we just use here the best model that we have here, so our linear plateau model, if you come on the next chunk, I want to call that model, so it's called mod4_linp. That is just the model itself. We're going to feed that into a function called intervals coming from NLME. And it has an argument for which. So which I want fixed. So I want to know the interval, the error around our fixed part of the model, which one of them is the breakpoint. So notice here that, and this is something I think Charles asked in a previous question on a previous class, as far as, okay, we have these point estimates, but do we have an error around them that we can use to understand the variability around it? So here, you know, if we were using this model, we would tell a grower that for that field and that year, the optimal sitting rate was 73,000 seeds per hectare, but it had an error that went from 66 to about 81. Right, so you provide a level of uncertainty around your point estimate for that grower. So this is the 95% confidence interval around that breakpoint. All right, so very interestingly now, if you think about it, this is the seeding rate that optimizes yield. But it does not tell us what is the actual yield at this seeding rate. We don't have, well, I mean, we could visually perhaps try to eyeball it, but we don't have that value yet. So maybe let's do that. So let me poke your attention perhaps. What function do you think we can use to know what is the yield level at this seeding rate based on the model that we have? Predict, right? Thanks, Usman. That's exactly right. So if you remember, every time that we were making the predictions on the ND, so I'm going to come here to the latest one, which was on the linear plateau. We're basically using the function predict, giving that the model that we want to use to make the prediction, and then giving all the ND values that we want for that. In this specific case, I don't want all those sitting rate values, all those 81 sitting rate values. I just want one, which is our optimal. So if I come back to my chunk here, we're going to use the function predict. We're going to call here our model, which was mod4linp for linear plateau. That was our best model that we decided based on the AIC table. It has this argument for new data. So really, I just need that prediction for one value. So instead of creating a full data frame for just one value outside of here, I'm going to do that kind of on the fly. So I'm going to use the function data.frame to create a data frame, where I'm going to have this column for SR_KSHA, which matches exactly how the model was trained, right? The model was trained with a column that had this name. And then I'm just gonna give here our breakpoint. So our breakpoint, our sitting rate that optimized yield was 73.48. Let's go with that. And then remember, we want to say level equals 0, so it does not try to give you an estimation for any given random effect level, which in this case was block. It's just going to give you an estimation at the level of the general level of the model. So if we run that, we get a yield prediction of 13.45 for this model. So at this sitting rate, we get a predicted yield of 13.45, which if you do go back to this plot here, if you were to draw a vertical line here on 73.40 something, and then make that line extend to the y-axis, you would find that value. That is the predicted value of this model, right? And remember that the model prediction is basically the line that we have right here. So that's what we're doing is we found out what was the optimum rate, and then you can tell the grower with this optimum rate, your yield is going to be X, estimated to be X. All right, so I think I have. We have a quiz today as well. I forgot about that. So I think I'm gonna skip this last chunk here. I was basically, if you just run what we have there, I was just gonna show you how to draw a line that would go from an optimum x-axis. So a line going vertically here to the breakpoint and then horizontally to the max yield level. It's just for visual purposes, but I think because we're running out of time, I wanna quickly skip that and go to and wrap things up here. Okay, so as a quick summary of what we did in this exercise, we use regression. So remember, this was the first exercise that we fully used regression. So our explanatory variables were also numerical, in contrast to ANOVA, when our explanatory variables are categorical or factor. We use regression to find optimal levels of a given input to optimize a given output. In our case, it was sitting rates, optimizing yield. In your case, it could be anything that you can think of that you increase some level on the x-axis and you expect a change on the y-axis, right? So we talked about some examples previously. I'm not going to do that again now, but it's really applicable to a lot of disciplines. And then always check your residuals, right? We really saw here first why we check assumptions on residuals and not raw data. And also how our residuals change as we're changing models. And the residuals themselves may give you some hints of how you can improve your regression model on what pattern you see in the residual. Maybe try to add that component of that pattern to your model and see if it looks better. All right, so before we go to the quiz, any questions here about what we did? So not about the exam yet, but just about this exercise.
Dr. Vestos.
Yes.
After I made the mistake in the code, I couldn't really follow after what you just said, so I'll have to revise this video.
Mm-hmm.
So I'm just wondering if the quiz is related to the coding side of this thing.
It's not related to the coding. No, it should be good.
Okay, thank you.
All right. Any other questions before our quiz? All right, I don't hear any, so let me make the quiz available. I'm gonna give you just 5 minutes and then we'll have 10 minutes to talk about the exam. Okay, so if somebody can just double check and make sure that quiz 5 is available to you.
Yes, it is.
Perfect. So I'll give you 5 minutes here and then we'll continue. All right, our time is up. If you're still working on your quiz, you're, I guess, welcome to work on it for, the next, I don't know, 5 minutes or so. I'm just gonna say here that we're at 11:08. So Aminder, is attendance open on? Okay, so make sure you claim your attendance. I'm gonna stay around to answer any questions you may have about the exam. And if you don't have any questions and you already claim your attendance, then you're good to disconnect or to go, and I'll see you on Thursday. A quick reminder is you will use the computer in your computer labs. You will not use your own computers. You will not have access to your material. It's a closed book exam, and it is on ELC. So make sure that you are familiar with how to open ELC on your lab computer, not on just on your laptop. And if you want to bring water, if you want to bring, a snack, is you're gonna have 2 hours to complete the exam. And yeah, I think that's it. So we're gonna still be connecting. I'm gonna be connecting here in Athens. I'm gonna be on Zoom. We're all gonna be on Zoom anyways. Just so I can answer any questions if you may have during the exam, but it is gonna be on ELC, again, with the computers in front of you from the computer lab and not your own computer. All right, I'm gonna just stop recording, but I'll stick around for another moment here if anyone has any questions.